Hello, welcome to the class. Today we have the topic Stereoisomerism, Chirality and chiral molecules, and RS configurational assignment to the chiral centers. First, let's come to introduction. Isomerism of molecules arises from different connectivity between atoms constituting them and different relative arrangements of the atoms in space. Stereoisomers have identical molecular formula and same connectivity of the constituent atoms, but the relative three-dimensional arrangements of the atoms are different. As a result, they possess different properties. The presence of chiral center in a molecule may impart the chirality character of the molecule, and existence is enantiomeric pairs. The absolute configuration of the atoms or groups around the chiral center is expressed in terms of RS nomenclature system of CIP rules. First, isomerism and isomers. Molecules having identical molecular formula may have different properties due to different atomic connectivity or different spatial orientations of the constituent atoms. The phenomenon is termed isomerism, and the molecules are called isomers. The three major classes of isomers are constitutional isomers, stereoisomers, and conformational isomers. Stereoisomers. Isomers having same atomic connectivity but differing in the relative spatial arrangement of the constituent atoms are called stereoisomers. From symmetry criterion, stereoisomers are classified into two major classes, enantiomers and diastereomers. Classical stereochemistry considers geometrical isomers as one class of stereoisomers. Now coming to enantiomers. Enantiomers are stereoisomers whose molecules are non-superimposable mirror images of each other. For example, enantiomers of butane 2-ol. Second one, enantiomers of 3-methyl cyclohexane. Now, these enantiomers are chemically alike is they have the same atomic connectivity and identical relative spatial arrangements of atoms in terms of distance and dihedral angle. They possess identical physical and chemical properties. They are different in their properties. However, towards plane polarized monochromatic light, chiral reagents, and enzymatic reactions. Now, coming to diastereomers. Diastereomers are stereoisomers whose molecules are not mirror images of each other. For example, the stereoisomers A and B of 2,3-dibromopentane are diisomers as they are not mirror images of each other. Second one, we have cis and trans isomers of 1,2-dimethyl cyclopentane. They are also diisomers as they are not related as mirror images of one another. Now we have this new term, chirality and chiral molecules. Some molecules like left hand and right hand are mirror images of each other, but they are not identical and not superimposable. A molecule or object is said to be chiral or said to possess chirality if it is not superimposable on its mirror image. A molecule or object that is superimposable on its mirror image is said to be achiral. To superimpose an object on its mirror image means to align all parts of the object with its mirror image. In doing so, the object can be moved and rotated, but it cannot be moved out of the plane. With molecules, this operation means aligning all atoms and all bonds, but bonds cannot be broken. For example, with this bromochlorofluoromethane, the molecule level A and its mirror image level B are not superimposable. No matter how you rotate A and B, all the atoms never align. Bromochlorofluoromethane is thus a chiral molecule, and A and B are different compounds. On the other hand, bromochloromethane is a chiral molecule because the molecule is superimposable on its mirror image. Now, relating to stereoisomerism, only the molecules possessing chirality exhibit enantiomerism, and the two compounds exist as a pair of enantiomers. From symmetry point of view, molecular chirality is exhibited by number one, asymmetric molecules, that is, molecules without any symmetry element except identity element E. For example, tetrahedral 1-bromo 1-chloroethane is devoid of any symmetry except identity element E, and this molecule is chiral in nature. We have amino acid cysteine is another example for this chiral molecule without any symmetry element. Secondly, we have disymmetric molecules, that is, molecules without rotational symmetry, Sn, I, and sigma. Biphenyl compounds with different bulky substituents at auto positions have C2 axis of symmetry, but no reflection symmetry, and such molecules are chiral in nature. Similarly, allenes with identical substituents at 1,3 positions show such molecular chirality. Stereogenic centers and chiral centers. The term stereogenic center or stereogenic atom is introduced to generalize the system of naming stereoisomers. It is defined as a center or an atom bearing groups of such nature that mutual exchange of any two groups in their arrangement around this center generates a new stereoisomer. For example, a carbon atom bonded to 4 different groups is a tetrahedral stereogenic center. We have this molecule bromochloroethane containing carbon atom bonded to 4 different groups. When the orientations of hydrogen and chlorine around carbon number 1 of molecule A are exchanged, a new stereoisomer B results. When the mutual exchange results in the production of an enantiomer, the stereogenic center is called a chiral center or chirality center. In the above example, the isomers A and B are enantiomeric pairs. The C1 is a chiral center. We have this drug thalidomide, a popular sedative and anti-nausea drug for pregnant women. It is a molecule with one such stereogenic center. However, this thalidomide was never approved for use in the United States as the other enantiomer, teratogen, was responsible for thousands of catastrophic birth defects in children born to women who took the drug during pregnancy. Now we have Taxol as a second example. It is 11 stereogenic centers. It is an anti-cancer agent active against ovarian, breast, and some lung tumors. Now, all chiral centers are stereogenic, but stereogenic centers are not chiral center. For example, in BUT2N, C2 and C3 are stereogenic centers, but are not chiral centers because exchange in arrangement of two groups at the carbon atoms produce a stereoisomer, but the new stereoisomer is not enantiomeric with respect to the first isomer. Hence, the presence of stereogenic center is not sufficient for a molecule to be chiral in nature. Even if chiral centers are present, the stereoisomer may not be chiral and not enantiomeric. For example, the mesoisomer of tartaric acid, it is not chiral even though there are two chiral carbon atoms. The molecule A is superimposable on its mirror image B and hence achiral in nature. For a molecule with n different chiral centers, there are to the power n numbers of stereoisomers possible, not including geometric stereoisomers of double bonds. If there are identical chiral centers, the number of possible stereoisomers becomes less. Now, mesocompounds. Mesocompounds are molecules that contain equal numbers of chiral atoms that are mirror images to each other and are achiral because they also possess a plane of symmetry. They are optically inactive because of internal compensation. The presence of internal plane of symmetry is shown below for meso 2,3-dimethyl-butane. With only one chiral center, there are always two stereoisomers and they are enantiomers. When there are more than one stereogenic center in a structure, diastereomers may arise. A pure chiral compound, not a mixture of enantiomers, interact with plane polarized monochromatic light and cause the plane of polarization to rotate to the right or to the left. Such stereoisomers are said to be optically active isomers or simply optical isomers. The term, however, is now obsolete if the angle of rotation is clockwise with respect to the initial plane of polarization. The rotation is said to be dextro or positive, and if anticlockwise, it is levo or negative. The prefixes dextro and levo come from the Latin dexter meaning right and levus meaning left. Enantiomers behave differently with plane polarized light because plane polarized light is composed of a right-handed and a left-handed circularly polarized component beams. The optical rotation is expressed as specific rotation. Specific rotation alpha at T degree centigrade and lambda equal to 100 times alpha by LC, where lambda is wavelength of the light, alpha is observed angle of rotation in degree, L is path length of the light, and C is concentration of the solution in gram per milliliter. Reznick modification. Optical rotation is an inherent property of an optically active compound and is used as a physical constant for characterization of the compound. A mixture of equimolar amounts of enantiomers will not show optical activity because half of the molecules would rotate light to the left while the other half would rotate the light to the right with a net rotation of 0. This effect is called external compensation. Such optically inactive mixture is called Reznick modification and is expressed by the stereochemical descriptor. Stereochemical nomenclature of stereoisomers with stereogenic centers now. Optical rotation depends on the relative spatial arrangement of atoms or groups around the chiral center, that is called absolute configuration. A naming system called the Kahn-Ingold-Prelog method, or in short CIP method, is used and it follows several rules. They are, number one, the chiral centers present and the 4 different atoms or groups attached to each chiral center are identified first. Priorities 1, 2, 3 or 4 are then assigned to the atoms or groups directly bonded to each chiral center in order of decreasing atomic number. The atom of highest atomic number gets the highest priority. Number 2, if 2 atoms directly bonded to the chiral center are the same, priority is assigned based on the atomic number of the other atoms bonded to these atoms. Number 3, to assign a priority to an atom that is part of a multiple bond, treat a multiple bonded atom as an equivalent number of singly bonded atoms. Fourth, if 2 isotopes are bonded to the chiral center, priority is decided by atomic mass number. Higher mass number is assigned higher priority. Number 5, after the priorities are assigned, the molecule must be oriented with the lowest priority group pointing away from the observer. After getting the correct view, a circle is traced from priority 1 to 2, 2 to 3. If this circle makes a right-handed turn, then the configuration is assigned R. The R comes from the Latin word rectus, meaning right. If the circle turns left, then the configuration is S, meaning left, which in Latin is sinister. A chiral carbon atom thus has 2 different designations, R or S, depending on the orientation of the substituents. The assignment may be described in the case of the chiral carbon atom of the enantiomers of butane to all as follows. The priority order of the 4 groups around the chiral carbon is: hydroxyl group OH is number 1, ethyl group is number 2, methyl group is number 3, and lastly hydrogen is number 4. The molecule is then oriented in such a way as to visualize it away from the group of lowest priority, that is hydrogen, and the other 3 higher priority groups are traced. The RS nomenclature is then assigned on the basis of the direction of the priority sequence 1 to 2, 2 to 3. The RS nomenclature is then assigned on the basis of the direction of the priority of the sequence 1 to 2, 2 to 3. Thus, the configurational arrangement of the atoms and groups around a chiral center in a molecule can be assigned this nomenclature system according to the CIP rules. Now, coming to the conclusion part of today's class, a particular molecular formula may correspond to several compounds referred to as isomers with differences in atomic connectivity and in configuration. Isomers with same atomic connectivity but different spatial arrangement of atoms and groups are called stereoisomers. Now, enantiomers and diisomers are the major classes of stereoisomers from symmetry criterion. Enantiomers are stereoisomers related is object and its non-superimposable mirror image. They exist as optically active pairs. However, diisomers are those stereoisomers which are not mirror image of each other. Molecules which are not superimposable on their mirror image are said to be chiral molecules. The absolute configuration of the chiral center in a molecule is expressed by RS nomenclature according to CIP rules. Stereoisomers of the biomolecules play a very important role in living organisms. This is reflected as an important and practical issue for bioorganic and pharmaceutical research area. So, these are all about stereochemistry of molecules. Thank you.